Welcome to my channel, Our Soils. And this video is about preparation of standard solutions, which plays a major role in our chemical analysis and or in the soil analysis, particularly as a soil scientist. We prefer more importance on soil science background. Let us see what is a primary standard. So, in any analytical laboratory, it is very most essential to prepare or to maintain stock solutions of various reagents. Some of this will be very accurate known concentration. So it is a nothing standard solution is nothing but we should know the accurate concentration, that is called the standard solution, and the correct storage of such solution is very imperative. That means it is very important. So whenever we are working in any laboratory, in any analytical laboratory, we should maintain some stock solutions. That is, those are the primary standards. So we should know the concentration, what is a normality, what is a molarity, or what kind of concentration it is, how much quantity it is. So we should know all those things, very important. So coming to the point, there are two types of stock solutions are there. I mean, two types of standards are there. One is a primary standard and another one is a secondary standard. So primary standard is naturally either it should be salt or some acid salts. It should have a very high purity that can be dried at some convenience temperature. And it should not be any decomposing, and that can be weighed in both high degree of accuracy. That means the molecular formula should be very high, and it should be very convenience temperature. It should be stable in any type of temperature. It should not go for any self decomposition. So those are called the primary standards. Coming to the secondary standards, this secondary standards is a solution which contains exactly known amount of the substance in a unit volume of solution, and which is expressed mostly in normality, molarity, and can be determined by titration against the primary standard. That is very important. So this secondary standard is prepared from this primary standard. Not exactly, I should not use the prepared. It is standardized by help of these primary standards. So we will take a deep look about the secondary standards, and there are some calculations are there, and we are going to prepare a normality solution in this lecture. Let us see very first we will see what are the primary standards. So before that, you see it is followed that secondary standards, the solution in which the concentration of dissolved solute has not to be determined from the weight of the component dissolved. See, this is very important. Remember this point. I'm reading line to line because these points are very important in coming slides. You see, the secondary standard solution is a solution in which the concentration of dissolved solute has not been determined from the weight of the component dissolved. Remember this point. But by reacting or titrating of a volume of a primary standard. So this is what I am saying. So always the secondary standards are always titrated against with primary standards. Now we will see how those type of standards are prepared. What is the type of standardization should be taken. You will see all those stuff in the coming slides. So before going that, we should know some criteria. So which type of chemical should be used for the primary standards? Let us see. Very first, it should have a high degree of purity. That should have a 100% purity, and its composition must be known accurately. We should know the composition very accurately. It should be very 100% pure. And second one, it should be capable of being dried at 100 to 110 degrees Celsius without undergoing any decomposition, and also capable of being cooled in weighing bottle inside the desiccator. It should be tolerate up to the 100 to 110 degrees Celsius. I should not go for any decomposition, also capable of being cooled in desiccator. So this is usually be done in laboratories. Whenever we keep any hot substance in anything in our hot air oven, we kept in our desiccator to avoid the moisture absorption. Let's see. And the third point, it should react stoichiometrically. Stoichiometry means capable of reading exactly as the equation indicates. So it should have exactly the equation should follow this stoichiometrically rules, with a solution to be standardized or with the substance to be determined. This third point is very important while we're considering any chemical as a primary standard. Now let us see the fourth one. It should not be hygroscopic or non-disquiscent. should have a I equivalent weight. Naturally, should have a very lengthy formula. Should have I equivalent weight. Why? Because weighing 30-40 grams is quite easy than weighing 1 gram, 2 gram in analytical balance. That's why you should have a very high equivalent weight. And coming to the sixth one, it should be soluble in common solvents, preferably water. Generally in soil science, we prepare all our solutions in a distilled water. If you want to be very cautious, we should go for double distilled water is preferred for preparing primary standards. And all the normality, formality, all this type of solution should be prepared in volumetric flask only, not in beakers or any other container. It must be stable in a common solvents and preferably water. I think same point is repeated. It must be stable both in pure form and in solution. So it should be very stable, whether it should be in a solution or it is in a salt form, whatever the form it should be very stable. It should not give any type of other secondary compounds, or it should not decompose it, which you have already learned. Coming to the solute purity, we have to learn what are the importance, what are the criteria for the primary standards, but also we should take care of solute purity. The concentration of primary standards need to be known accurately. We should know the accurately. Therefore, the solute must be pure. And to ensure this, the following guidelines should be followed. So we have read what are the guidelines is needed for the primary standard, but also at the same time, we should take care of some other aspects. What are those? Let us see. When we're using any powder, naturally, most of these most of the primary standards, primary chemicals or primary standard chemicals will be in powder form, or sometimes we go for a crystallized reagent used as and we should use whenever we are using any powder or a crystallized reagents, use a clean spatula to transfer the reagent from its container to the weighing board or weighing container, whatever you call weighing container. If you're weighing out too much, for example, if you want to take a 40 grams, if you added some 42 grams, what you do? Don't take that excess amount of chemical back to your bottle. That's not advisable. Okay. If you weigh out too much, do not place the excess back into the container. So you should discard the extra. If absolutely necessary, if it is too much, we have to go for it. Means we have to use a very clean spatula to break up the clumps of chemicals. You should go for clumps. Yeah, the clean spatula to break up the clumps of the chemicals. So if it is necessary, we have to touch our spatula of the chemical. Means you should use a very clean spatula, and we should break the clumps of the chemicals. Let us see. Coming to the next point, solute should be an analytical reagent. Should be AR grade only. We should use only AR grade for preparing any primary standard. We should use only AR grade. Solutes should be dried before being weighed and made up to the volume required with the solvent. So exactly, we have to take exact amount of solute and we have to put the same amount in our required amount of volume in the solvent. So in one point, students, primary standard is nothing but it's a known exact quantity or concentration of a solution. Right, coming to the preparation of primary standard. Now let us see how we have to prepare a primary standard. Here I'm taking sodium carbonate, which we usually use in soil science. Mostly we use only sodium carbonate as a primary standard, but we can go for many other primary standards are there. But here I'm taking an example of sodium carbonate. Let us see what is the molecular weight of sodium carbonate. It is 106 grams, which we know, and its valence is 2. And we have to find out the equivalence weight of sodium carbonate. Why equivalence weight of? Because here we are preparing normality. We are preparing a normal solution. So what is the definition for the normality? It is a 1 gram equivalent weight in 1 liter of solution is called normality. So that's why we are taking an equivalent weight. Equivalent weight of sodium carbonate is molecular weight divided by the valency. So we know the molecular weight is 106 grams and the valence is 2. So 106 by 2 is equal to 53. That means we have to take a 53 grams, right? We have to take a 53 grams. Let us see, therefore, 1 equivalent weight of sodium carbonate is equal to 53 grams. That means, therefore, 1 equivalence weight of sodium carbonate, how much we will get for 1 normal solution? We have to dissolve 53 grams in 1 liter. It will get 1 normal solution. There's 1 normal solution we will get. So if you're not interested, you want to prepare for 0.1 normal, This is what today we are going. I'm going to explain taking with this example. I'm going to explain all your coming slides with this 0.1 normal solution only. So 5.3 here, it's 53 grams in 1 liter will give us one normal solution. If it is 5.3, it gives around 0.1 normal. So if you want 0.1 normal solution, we have to go for 0.53 dissolved in 1 liter of solution. I will give solution. So no, sir, I'm not interested to prepare 1 liter. I need 250 ml. You can go for 1.325 grams dissolved in 250 ml. Will give us a 0.1 normal. All these things should be done in volumetric flask only. If you are preparing 1 liter solution, you have to prepare in 1 liter volumetric flask. If you're preparing 250 ml, you should go with a 250 ml volumetric flask. So this is the condition. So after preparing, after dissolving all the chemical sodium carbonate in our distilled water, make up the volume up to the lower meniscus. As it is a transparent solution, we will go to the lower meniscus. Then we are prepared. Primary standard is ready for us. So these are the important things. So 53 grams in 1 liter will give us 1 normal. So if you are interested in 0.1 normal, it is go for 5.3. We get to give 0.1 normal. So 1.325 grams in 250 ml gives 0.1 normal solution. This is regarding the primary standard solution, preparation of primary standard solution. Coming to the second preparation of secondary standard solution, which is very, very important and very crucial in this lecture. Let us see here, you can see this image. I am putting this here. This is the distilled water. This is an acid. Remember, students, we should be very careful that always add acid into the distilled water. Don't add water in distilled water. It is not advisable. Always add acid in distilled water. Is a common thing. Now let us see how to prepare a secondary standard solution. Very first, I'm taking an example of sulfuric acid, which I mentioned in my image. So what is the molecular weight of sulfuric acid? It is 98.079 gram per mole. This is a molecular weight of sulfuric acid. As usual, we are preparing a normal solution. There is a normality solution. So equivalence weight of H2SO4 is equal to same formula. Molecular weight by valency, that is 98.079 divided by 2. The valency of H2SO4 is 2. That is equal to 49.039 gram per mole. We get it. Okay. Now, one equivalent weight of H2SO4 is equal to 49.039. Remember, it is a gram per mole. So if we mix 49.039 grams per mole in 1 liter, we get 1 normal. But still the problem is not solved. We have a liquid, not a gram. We didn't have any salt. H2SO4 is in liquid form. So we have to do further calculation. So specific to prepare this 1 normal solution, we have to know the specific gravity of concentrated sulfuric acid. What is the specific gravity? Is nothing but it is a 1.835. The specific gravity of sulfuric acid is 1.835. And 1 gram equivalent weight, our equivalent weight is 49.039. Now let us see, and also we need a percent purity, that is almost 98% very pure sulfuric acid is there. Almost we get a 98% pure solution we will get in our container. So 1 liter of 0.1 normal solution. Remember, this is for 1 normal. This is for 1 normal, 49.03 gram per mole in 1 liter will use 1 normal. But here I'm taking an example of 0.1 normal. It is around 4.903. Right? It is a 4.903. So it will give 0.1 normal. Just I pulled my decimal to forward. So it is if I pull my decimal to forward, it is a 0.1 normal solution. So now I'm taking an example of 0.1 normal. Remember, students, or remember, folks, whoever listening this video, I'm going to explain all my calculations by taking 0.1 normal T solution only. Now going for a calculation, let us see for 4.903 gram of H2SO4. Now we have to find out the purity of this solution, that is 100 into 4.903. That is nothing but your 1 liter contents. As I said, I'm preparing 0.1 normal solution divided by 98, the percent purity divided by. So it gets 5 grams. Remember, I get 5 grams. It is not converted into volume. So our sulfuric acid is a volume, not a salt. So to overcome this problem, we have to know, or we have to divide with a specific gravity. Let us see that 5 grams divided by 1.835 is equal to 2.724. So if we divide it by our 5 grams, the so-called 5 grams in percent purity divided by 1.8, this is a specific gravity. See, this is a specific gravity. This value is specific gravity is equal to 2.725. How much is this? Now here we get a volume. So this much amount of 2.724 ml of volume of acid should be added in 1 liter. We get 1 normal H2SO4, our strong acid. No, naturally H2SO4 is a very strong acid. So if we add a 2.724 ml of acid of H2SO4 in 1 liter, we get 1 normal solution. This is overall for the preparation of 1 normal solution. This is how we prepare a 1 normal solution. So therefore 2.724 ml in 1 liter of distilled water gives 0.1 normal. Remember students, I'm taking 0.1 normal, not for 1 normal. So if you want to prepare a 1 normal, instead of 49.03, just put 4.903 instead of 4.903, you put 49.039 here. You get up to 1 normal. Now, simply, if you want just instead of 5 grams, you will get a 50 grams if 1 normal. Okay, but I'm taking an example of 0.1 normal. So overall, it is a 2.724 ml in 1 liter of distilled water gives 0.1 normality solutions. But here there is one problem. What is that? Can we add exactly 2.724 ml of H2SO4 acid in 100 ml of distilled water? Is it practically possible? Can we exactly? No, as it is a concentrated acid, we cannot pipette. It is not advisable. It is very dangerous. We should not use any pipettes. It's very difficult also. We can't get an exact amount. So practically not possible. So practically it is not important. It is very difficult to add exact amount of acid in 1 liter. So practically not possible. There are certain calculations to adjust the normality of secondary solutions. So what are those calculations? Remember students, here there is a tricky questions. We can't add 2.72 ml in 1 liter. Practically, it is very difficult. Instead, what should we do to overcome this problem? Here is the solution. So remember students, instead of adding 2.7, that's a certain ml of acid, we will add an excess amount of acid, or sometimes we will add, remember, if we add excess, usually in laboratory, we will advise to add more acid. Instead of 2, we will advise or we will add a 4 ml or 5 ml. Why? Because if we get a more normality, if we get a 0.9 or a 0.8 normality, we can add water to that. For your understanding students, remember there is a 2 beakers are there, or 2 glasses are there, right? Right, I'm prepared one juice, some sugar syrup I have prepared. So most of my guests prefer, okay, I need only certain very normal sweet. So instead of they said I need only 10 grams of sweetness. So what I did accidentally, I added 15 grams. What will be the condition? The sweetness will be more. It will be very sweety, very sweet. Okay, to avoid this, what we will add to bring this 15 gram sweetness into 10 gram sweetness, what we will add? We will add some water. We'll add some water. So while we add water, what will happen? The volume will be increases. The volume will be increased. For example, here I taken only 500 ml. So to reduce the sweetness, if I add more water, say for example, I add 200 ml of water. So what will happen? The 500 ml water, I get only 700 ml of water I usually gets. Right? So same thing was happening. Same thing in reverse. If you think ulta, if you think very reverse more way. So my guest said he needed only 10 grams of sugar in his juice or sugar syrup. I add only 5 grams. What happened? He said, oh, it is not so sweet. I need some amount of sugar. So what we'll add? We will add sugar here. Here also we will add a sugar and we will mix it. But you remember, how can we manage, or how can exactly we know that, how can we calculate, or can we reach to his expectations? Exactly, I need exactly this amount of sweetness, I need this amount of sweetness. It's very difficult. So what we will do, what we will do in home, we usually taste, taking one spoon of juice, we will taste it. Then we will come into some conclusion, oh, this is very sweet, or some sweetness is very less. Same thing will be happen in our chemistry lab also. What we will do, same thing will be happen in our chemistry lab. We will titrate with our primary standard solution. Exact amount, to check the exact amount of normality, or to know whether it is exactly 0.1 normal, or exactly it is less than 0.1 normal, or it is more than 0.1 normal, we have to do titration. So what should we do? We should take the sodium carbonate in our burette stand. We should take the sodium carbonate in our burette stand, and the prepared solution, the so-called, we prepared now some 2.7 ml of acid. If we add in 1 liter, we will get some one normal solution, which is theoretical part, which we have seen in previous slide. So what will happen? We have to titrate it, as we discussed. We have to titrate with our primary standard solution. So now here we will see some practical examples. So this is the table format. So whenever you go for a titration of primary standard solution or secondary, not primary, secondary standard solution, we have to prepare this table. So here we are preparing again H2SO4 against sodium carbonate. This is a primary standard. This is a secondary standard. As I said in my previous slide, we have to standardize the secondary standard solution with our primary standard solution by titration. So in burette stand, we will take sodium carbonate as a primary standard. In our volumetric flask, we have to take 100 ml of volumetric flask. We will take H2SO4. So what I'm doing, I will take very first, I will take 10 ml from pipette. I pipette out 10 ml in my volumetric flask. In my volumetric flask. Then we will go for initial reading. That's so initially it will be 0. Naturally, we will fill the burette up to 0, and we'll get 8.2. Again, we'll get 8.2. But to get a concurrent value, better go for 3 times. But here I'm doing only 2 times. Second time we go for 10. Again, I will start from final point 8.2. It will I have ended up with the 8.2. So here in this titration, we have to be careful that we have to use methyl orange indicator, and the endpoint will be from pinkish red to straw yellow color like this. So naturally, we are using acid versus base, base versus acid. So we have to go for methyl orange only. Methyl orange indicator is very important. So when we add an indicator in our acid solution, there is 0.1 normal H2SO4. It will show this color, pinkish red. So when we titrate it against with sodium carbonate, it will turn into straw yellow color or this pale yellow color. So now our value is 8.2. So we get the concordant value of 8.2. Now let us see how this 8.2, how we are, whether we have to check whether our 0.1 normal is a 0.1 normal solution is exactly 0.1 normal or some excess amount. Let us calculate. So normality of our, that's N1 is, our N1 is 0.1 normal. So our sodium carbonate, our main primary standard solution, we know we will take it as N1, that is a 0.1 normal, and volume of sodium carbonate consumed is V1, that is equal to 8.2. That means this one, the titration value. 8.2 is nothing but your titration, that is a volume. So we know the normality of sodium carbonate, and that is N1, and volume of sodium carbonate consumed is V1 is equal to 8.2. Now let us see normality of H2SO4. We think it is a 0.1 normality H2SO4, but we don't know exactly it is a 0.1 normal or not. But exactly we don't know how much it is. Let us see normality of H2SO4 pipetted. That means the solution which we prepared in a beaker that we had it na 2.1 to 2.7 ml, whatever we added, 10 ml. We have taken only 10 ml for titration, but we have taken twice, right? I will say when we will use this to 20 ml. Now we're coming to our normal equation. N2V2 is equal to N1V1. This is our equilibrium, chemical equilibrium value. So here we have N1 value, V1 value, N2 value, and V2 value. But remember, we don't know N2 value. It is an X. We taken as an X. We don't know. So N2 is equal to N1 into V1 into 2. What is N1 here? This is the calculation. N1 is nothing but your sodium carbonate, 0.1 normality into sodium carbonate consumed as 8.2 divided by 10. This 10 is nothing but how much amount of ml you have pipetted, 10 ml. And here you can ask my question, so we have used 20 ml. No, we should not. For calculating the concentration, how much concentration it is, you have to put only one titrate value, 10 ml. We will use this to double 10, 20 ml in later coming calculations. So coming to the calculation, 0.1 into 8.2 divided by 10 is equal to 0.82 normality. Remember, is it less than or more than 0.1 normal? It is, as I shown in my top heading, it is 0.1. It is less than 0.1 normality. So as I said, what has happened here? The concentration is very less. The acid was very less. So to avoid this, what should we do? We should add an acid. We should put an acid in it. But remember, students, dealing with acid is very difficult. Dealing with distilled water is very easy. So now it is a 0.02 normality was less than 0.1 normality. So acid to be added. Here it is a very less than normality. So acid to be added. So therefore, there is a calculation 2.724. This is a volume of acid which we think we have added, but we have added very less than 2.724, because that is why we get only less normality into 0.02 normality. This one, the calculated value, divided by 0.1 normal, your primary standard normal, into 1000 minus 20. 20 where? How much amount of, how much amount of total titrations? The total. So here we have used 2 times. So 10 plus 10, 20. So 22 times I have titrated with our secondary H2SO4, 0.1 normal H2. So I am put 20 divided by 1000. Where this 1000 came? So this 1000 is nothing but the volume which we are intended to be maintained, which we need is the 1000 volume. That is, this 1000 is nothing but the volume, total volume which we are preparing. So here we are preparing 0.1 normal H2SO4. That is equal to 2.189 ml of acid. So we have to add another 2.18 ml of acid to the water. Then only we will get, to adjust this 0.1 normal to H2SO4, or to bring this 0.08 normal to 0.1 normal, we have to add another 2.189 ml of acid. You can ask, sir, it is somewhat almost equal. What is the difference? But already we have removed some volume. Here we were calculating only for 980. 1000 minus 20 is a 980, right? 980. Okay, we get 980 ml minus 20 by divided by 1000, we get 2.18 ml. So this much amount of acid to be added in our prepared solution. So conclusion is nothing but 2.18 ml of acid to be added to correct the normality of 0.1 normal H2SO1. 0. Not correct exactly, we think it's 0. But we get how much we get? We get only 0.082. So we get 0.082 normality only. To bring the 0.0282 normal to 0.1 normal, we have to add 2.189 ml. When we have to add, when what is the condition here? This is the condition. If it is less than 0.1 normal, so we have to calculate this N2 N2V2 is equal to N1V1, or N1V1 is equal to N2V2. So while we calculate it, if we get this one, if it is less than 0.01 normal only, we have to go for addition of acid. But as I said, dealing with acid is very difficult. Even adding but this amount of ml of acid in our distilled water is very difficult. So practically it is very impossible. It is very difficult. Exactly, we can't add. So to avoid that, as I said previously, we will add more acid. We will add more acid, as again my example of sugar and water sugar and water example. So we'll add more acid and we will add distilled water. So adding distilled water is very easy when compared with adding acid. Now let us check this. If your value is more than 0.1 normal. So for example, as I said, if we add more acid instead of 2.7 ml, as I said, if you add 3 ml, 4 ml, if you add a more amount of acid, what will happen? It will go for beyond that. It will go beyond the 0.1 normal H2SO4. Same table is repeated here, but with a different concept. See, the same thing I have titrated 2 times. I have titrated. As I said, here is a burette solution is nothing but your primary standard sodium carbonate, and your aliquot is nothing but H2SO4. Your 0.1 normal H2SO4, which we think it is a 0.1 normal, but exactly is not possible. So we have to titrate with titrate our secondary standard. Secondary standard here it is H2SO4. Our primary standard is sodium carbonate. So we have to titrate our secondary standard with primary standard. Here it is a condition. If you add a more acid, what will happen? See here, my titration value is 13. So I did 2 times. So I get a concurrent value of 13. Same indicator we use here also. Some very possibly when we add it very early, it is a pinkish red. When we titrate it again, it comes up with the straw yellow. So this is the condition here. So now check the calculation. Same thing, students. N1 V1 is equal to N2 V2. We will calculate this simply. N1 is 0.1 normal. Your this thing, your primary standard normality into 13. This 13 divided by 20, not 20. It is 10 only. Some sort of mistake. It is 0.1 normal. So we get 0.13. We get 0.13 normality, not exactly 0.1 normality. So here the condition is we have added more acid. So to reduce this high normality, we have to put acid. So the normality is more than 0.1 normal. So we have to put some water. So water should be added. Let us see that. So for this also there is another formula. Your titrant value minus 10 divided by 20. 20 is nothing but this 20. 2 times we have titrated into 1000 divided by 22. Why I have taken 22 means, student, why I have taken 22 means this excess to 2 ml where it comes means for rinsing, for cleaning my for cleaning purpose, we may use some solution. Here I'm taken 2 ml excess ml. That's why I put 22. Even if you go for previous calculation also, you can add, or if you use any excess solution for cleaning purpose or for rinsing purpose, you can add it. So 1000 minus 22. Now, so I substituted my value 13 minus 10 divided by 20 into 1000 minus 20 is called, I get 128 ml. So here we get here the conclusion is that we should add 120 ml of water is to be added to prepare a solution to adjust the normality of H2SO4. So the normality here we get is for 0.1 normal, 0.13 normal, right? But to bring this 0.1 normal into 0.1 normal, we have to add 128 ml of distilled water. So the the thing is to remember here, in calculation, in theoretical part, we get 2.7 ml of sulfuric acid to be added in 1 liter, then only we get 1 normal. But practically, it is not possible to add 2.7 ml. So what we will do, we will add an excess amount of acid. We will add some 3 ml, 4 ml. Why I'm saying add excess amount of acid? Because adding a water in the solution, it is very easy than adding adding a water in acid is very easy than adding acid in the solution. Now, adding 2.1 ml of acid is it is also not possible. It is not possible. So adding 120 ml, 128 ml of water is very easy, and exactly we can get. Again, we will backtitrate. Again, we will titrate it. We will titrate and we will check it. We have to cross check. After adding this 120 ml of acid in our so-called solution, 1000 ml solution, again we have to titrate with a primary standard, that is sodium carbonate. Again, we have to add indicator of a methyl orange. Then we have to calculate. We have to go for all these procedures, all these legal procedures. If we get 0.1 normal, then exactly our 0.1 normal solution is ready. I hope these calculations are very fundamental in our soil science laboratory. Hope everyone got some basic fundamental knowledge, how to prepare, what is the primary standard, what is the secondary standard, how to prepare 0.1 normal of H2SO for all this stuff. So with this, I'm ending my lecture. Thank you very much. Please subscribe to my channel, Our Soils, and please like this channel, like my channel, and please encourage. Thank you very much for kind cooperation. That's all. Thank you, and happy Teachers' Day to all my teachers. Thank you.